if we have, for our roots or our zeros, if we have -2 and +3, how would we set the work up to find the polynomial for this? Mm-hmm. And then if we multiply this out, we would end up with x squared minus 3x plus 2x, and then minus 6. Now this is a polynomial because all the coefficients are real, all the exponents are integers, positive integers, so this is a polynomial. Let's say instead we had for the zeros -5 and I. So what would this look like? Plus 5 and x minus I. So if we multiply this out, we would get x squared minus ix plus 5x minus 5I. Is this a polynomial? Why not? What's not real? Yes, the coefficients and the constants have to be real numbers in order for it to be a polynomial. So this is going to create an issue. If we have a complex root, right, or an imaginary root, if that happens, right, then the problem is that if we multiply it out, we're going to get an I in our polynomial, which means that it's not a polynomial. But there's an easy fix to that, and that is if you have the conjugate. So instead of just having -5 and I, let's take a look if we had -5, I, and -I. Okay, so what would happen is we'd have x plus 5, we'd have x minus I, and we have x plus I. Now this looks similar to a minus b and a plus b. What's the advantage of having this set up? And then we get a squared minus b squared. Everybody okay with that? Right? So this is nice because every time you do have these two roots, we actually end up with the difference of squares. And the convenience of that is that we can kind of skip multiplying everything out, and our a is x, and our b is I. So, and then we know I squared is really -1. So it ends up being x squared plus 1. Okay? But then we still have the x plus 5. And now notice if we multiply this out, x squared times x squared times 5, and then 1 times x, 1 times 5. And now is this a polynomial? Polynomial? Yeah, all the coefficients are real. All the exponents are positive integers, okay? So that brings up the situation then. If you have a complex or an imaginary root, okay, so let's say that a plus bi is a root of the equation, then its conjugate must also be a root. This is a theorem that you are going to have to remember, the conjugate pairs theorem, because what's going to happen is they will not give you the complex root and its conjugate. It's only going to give you one, and you have to know that the complex conjugate is the other. So these first two examples are, for example, 2 here, A and B. These are pretty quick examples because here it's telling you that you have a degree of 4, okay? Well, from 5.5, I had mentioned whatever the degree is, that's how many total zeros you have, okay? So we have 1 here, we have 2, and we have 3, but how many total are we supposed to have? We're supposed to have 4. What is our missing 0 here? 2 plus I, okay? So this is the 4th one. All right, because if you have a complex number, all right, so in this case, since 2 minus I is a root, then its conjugate, 2 plus I, must also be a root. All right, everybody try B. So we're trying to find the remaining zeros. In A, we were only missing 1. So this is the answer to A. So you guys are trying to find the answer to B. Yeah?
If something's called a theorem, does that mean that it's been proven?
Mm-hmm.
Is conjecture when it's not?
The postulate. A conjecture is like when you see a pattern and you say that you think something, and then you would go on to like try to prove it. So they give us 4 roots. What is the 5th root going to be? Negative I. So we had a positive I here. So its complex conjugate is negative I. And what's the 6th one going to be? Negative 8 plus 5. So the 2 complex conjugates.